it's much beyond that. So, can't be contained within a patent. So this is a mini lecture on functional uncertainty propagation. So I actually can't go long because I have a meeting at 4 that I have to get prepped for and Skype into. So I can't go long. So I'm really just going to do this as a mini lecture on functional uncertainty propagation. So if you measure some quantity, oftentimes you're doing so that you can estimate another quantity that's functionally dependent on it. Let's say you had a cube.
And it had temperature in it.
No. No temperature. Sorry, dude. So you have a cube, and you want to measure the volume of this cube, okay? And you have yourself a tape measure, and you're like, okay, I know cube. You're like, what the volume? You probably want to measure 3 sides, make sure it's actually cube. But just bear with me. Say you wanted to, you had a cube, and you were like, let's measure. Whoa, there's another side to that cube. Let's measure the volume. Let's estimate the volume. Now, you can measure a side of the cube, L, and then I know you could compute V as a function of L equals L cubed. I know. Geometry, or whatever this is. Geometry, yeah. Good old-fashioned geometry. So this is your functional dependence. So you aren't measuring the volume directly. You're measuring the length of a side, and then you're computing what the volume is from that. Now, the question is, if you have an uncertainty in L, UL, how does that transform into an uncertainty in V? So you have UL, it's estimated maybe using the RSS methods, design stage, or maybe even a more advanced analysis that we'll learn. But you have UL, and you want to know what is the uncertainty you should have in the volume. So remember that the uncertainty is an estimate of, so say like a mean value plus or minus this uncertainty value with some confidence, right? That's the uncertainty in UL. This defines an interval. So from L minus UL to L plus UL, right? It's an interval, if I ever saw one. So what you want to know is how that turns into a new interval, right? And what you can do is actually you can literally just plop this in as a function into, you can essentially compute the 2 limits on the interval in your estimate of V. So V, you drop in L minus UL for the lower bound, and then you drop in L plus UL for the upper bound, and you can compute this same interval. So I'm going to represent this as, we'll call it V lower. I'll call it V1 and V2. V1 and V2. Okay? So the lower bound and the upper bound. Now, unfortunately, when the function that you go through is nonlinear, this doesn't come out symmetric about the best estimate. So this interval was symmetric about L, right? So symmetric about L. In general, this is not symmetric about its best estimate, which would be V of L bar. Okay. So it's not symmetric anymore. I think I can prove this to you by drawing this. Say you had your L, and say you had your V, and as I recall, L cubed looks something like that. So if you were to, say, look at this operating point here, say this was your L bar, and this then was your V bar, or V of L. V bar equals V of L bar. Then your interval here is symmetric, but it comes up, intersects there, and gives you that value. This one comes up, intersects way up there, comes over here. So this interval is like, you know, even worse than this, but it should be centered. It's totally not centered now, right? Nonlinear gives you asymmetric intervals. But what's the uncertainty then? Because the uncertainty is just half of the interval, but the interval is assumed to be symmetric. So what's your uncertainty? The way people do this is to essentially make a linear approximation of the function at the best estimate value. Call it the operating point. Yeah, and then if you use a linear function to go through, then it comes back out as symmetric. So if you had this same interval, it would, the lower bound would come to here, the upper bound would come to there, and it's symmetric. Now, if that bound's too big, if the nonlinearity is significant like it is here, and that bound's too big, then you're going to be wildly inaccurate, right? So it's not a good estimate when you have a bound that is significant in relation to the nonlinearity of the system. So you have to be cautious with it. But roughly speaking, the way of dealing with it is take the derivative there and evaluate it at that point. If you have a function that has multiple quantities, say you're trying to estimate the density of this cube, the mass divided by the volume, as I recall. So the mass is a measurement of, the volume is a measurement of, so this is a function of two variables. So what do? You take the partial with respect to each, and that gives you your new value. So let's call the slope of this theta. And for each parameter, you're going to have a slope at the operating point. Call them each theta I. If the slope is theta I, then, and the uncertainty is this deviation from that point, then the uncertainty in your functional dependence contributed to from the ith variable is the slope times the uncertainty in your variable. So each one contributes theta I times your uncertainty in I. Okay? Theta I is the slope in its multiple functions. Theta I is equal to the partial of whatever the function is, so v in this case, d whatever the variable is. So if the variable is called x, the xi. So you take the partial with respect to that variable at the operating point. That's the slope. That's your what's called sensitivity. Bam. So you have a lot of uncertainties, depending on how many variables you have. So this one's got 2 uncertainties. This one only had 1. 1, 2. So what do you do if you have multiple? You guessed it. Root some square of them. So if you want to know the uncertainty in your function, all you have to do is take the square root of the sum of all of them, differentiate with respect to each variable, and multiply that by the uncertainty of each variable, and add them up. And you have yourselves
And square.
an estimate. Oh yeah, you should square that. Thank you. That part's kind of important. Yeah. So that's literally the whole deal. And we did it in 10 minutes. I thought I could do it in 5, but I was a little off. Does that make sense? People, I mean, I kind of like this way of lecturing. It's kind of fun. I don't feel like you guys got, like... Now, I feel like I may have given you guys, the impression that it wasn't too bad and you understood it. Hopefully. That was the idea. But I feel like when I lecture from the notes, it's a little bit better just because you guys have something to go back to. A little bit more concrete. I'll upload this as a video anyways. The real, we'll call it Old School Wednesday. Also Flannel Wednesday. Also, I'm going to call it Nice Christmas Sweater Wednesday. Yeah. All right, I got to go do another meeting thing. See ya.